A stationary point is when the function, in this case, the function with respect to x, is flat. So if a hike goes this way, okay, it's going down, 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 and then it reaches a flat place in the function. That's what a stationary point is. When the function is not climbing or going down, it's just flat. And in this case, the function is flat at 6. Okay, so what can we say about the derivative of the function at that point? We can say that the derivative is 0 at that point. And if we jump a little bit back from that point, that's 6, let's say at 5, what's the derivative at that point? What's the slope at that point? Is it positive, negative? Well, the slope is going down, negative. How about here? Is it positive or negative? It's positive because it's going up. You have to climb in order to continue. So it's positive. So we're left with negative, 0, and positive. Okay, so that would be your clue as to what kind of stationary point this is. So if you see that the derivative a little bit behind it is behind the stationary point is negative, and then it goes to 0, and then it goes positive, it is a minimum. Alright, let's just quickly check out what the derivative of the function is doing. We know that it's 0 here, it's positive here, and it's negative here. So we can draw a line like that. You can say this is what the derivative would be doing. The derivative of that function would be doing. Let's say that this is the function f of x. We're gonna see what's happening on the stationary point at 8. The function is flat, so the derivative at that point is 0. A little bit before it, it's positive, it's going up, so it's positive. A little bit after the stationary point, it's going down. You would be walking downhill, so it's a negative. This is how you identify a maximum. The derivative goes positive, 0, negative. So it's positive here around the 7. It's negative here around the 9. This is kind of what the derivative would look like. The important thing is that it's going to cross 0 at this point at x is equal to 8. Yes, sometimes it's not a line, sometimes it's another type of function like a polynomial. But the important thing is that it crosses 0 when the derivative crosses 0 when the function is flat. When the slope of it, the gradient, is 0. A third type of stationary point that I'm going to talk about is the positive inflection. This is where the function has a positive slope, the slope reaches 0, and then it goes positive again. That's the feature, that it goes positive slope, 0, and positive again. So if you're a climber, climb up the mountain, and then you find a plateau, and then there's more to climb. That's a positive point of inflection. The stationary point is at 7, so we know that derivative is going to be 0. Take a step back at 6. What is the derivative doing? It is positive. So at 6 it's positive, and then it goes to 0 there. At 8 it's positive again. And this is going to indicate to you that this is a positive point of inflection. So if the function is flat at 7, then that means that the derivative is going to be 0 at 7. This last type of stationary point is called the negative point of inflection. Functions that have this type of stationary points look sort of like this. So here at 6, the function is flat. That's what a stationary point means. The function is not rising, it's not falling at that point. It's just flat. If you're walking, it takes no effort to walk. You're not going up, you're not going down. The derivative of the function at that point is going to cross 0. If you take a step back, what's the slope of it? The slope is negative. If you take a step forward, slope is also negative. Let's look at what the derivative of the function. So this is the function here, fx. So what's the derivative of the function is going to cross, it's going to be at 0 at the point 6. It's going to be negative around here, negative, and negative around here. Yeah, it's going to do something like that. At 6 it's going to be 0, but it's not going to go into the positive side, this derivative f dash x.